in the continuation of this section, we are first going to talk about arithmetic means. You learn about geometric means back in geometry. This is something different. So arithmetic means are terms between two non-consecutive terms in an arithmetic sequence. All right. So if you have an arithmetic sequence, and suppose like, I just happened to just randomly pick that term, and then I picked another term which is non-consecutive, so not the one right after, like somewhere down the line. Oh, suppose I picked the 47. The numbers that come between the two that I picked are the arithmetic means between 7 and 47. Okay? So that's what it means. So now, let's take a look at this one. So now, if it's an arithmetic sequence, right? What was an arithmetic sequence? It's one where you do what to each number?
Add exactly the same thing.
Right, you add the same term to each number, right? Right, and since there is that like clear pattern, we can figure out these terms very easily. So let's just take an example here. So it says to write an arithmetic sequence which has 5 arithmetic means between 6.2 and negative 1.6. Okay, so what does that mean? There is this 6.2, and then there are 5 arithmetic means, right? So 1, 2, 3, 4, 5, and then it's negative 1.6. No, not necessarily, because if your D is positive, then the numbers go up. If your D is negative, then your numbers go down. Okay? Okay. It does matter. It needs to go in the proper sequence because that's how D will, that's the difference between D being positive and D being negative. So we take the sequence as is. And it makes a huge difference when, we're doing the series because the numbers are either going up or they're going down. So that can make the difference between the series adding up to 1/3 or infinity. Yes.
Divide by 7, so you
okay, so here's what, yeah, exactly. Right? So here's what we're going to do. So 1, 2, 3, 4, 5. And then it's negative 1.6. Okay. So basically, however, there are lots of ways to do it. But let's go with the formulas that we've been given. So what do we know here? We know what A1 is. It's 6.2. We know what AN is. That's the last term. It's negative 1.6, right? So AN always represents last term. Do we know what N is? Do we know how many numbers there are? 7, because it's the first, the last, and then the 5 in the middle. So let's see if we can figure out what D is. So now if from the 6.2 to the negative 1.6, if it's 6 steps, right, and we have to add the same number each time, then we can, basically just add and divide, right? So look, AN is A1 plus N minus 1 D. Okay? So negative 1.6 is 6.2. 7 minus 1, which is 6, D, plus. So I'm going to subtract 6.2. So I'll get negative 7.8 equals 6D. And then D is negative 1.3. Okay? So that's my D. That means at each step, I need to add D. So minus 1.3, that makes it 4.9. Minus 1.3, minus 1.3.
Would you just make the mean?
You can. Hang on. And then negative 0.3, and lo and behold, negative 1.6. Okay? All right? Now, if you could figure out that, these are incremental steps, And basically, what are we doing? What did you mean by the mean, Eli?
The mean between 6.2 and, wait, did I say the wrong thing?
No, you're right. I was
The
rhyming.
difference between 6.2 and negative 1.6, you'd add them and then divide by 6.
Right. So essentially, we're going from 6.2 to 1.6 in equal increments of 6, right? In equal increments, in 6 equal increments.
7.
So,
6.
well, yeah. So there are 6 steps basically to get there, right? So what you could do is you could, add these up. 6.2 and 1.6 is 7.8. Divided by the 6 steps, and you get 1.3. But now you have to remember, D is negative 1.3 because it's got to go down. Okay? So essentially, that's what this made us do. It made us add, divide, and then, but the thing is, when you do it this way, it fixes for the negative. Okay? All right. So that's arithmetic means. All right. Now, let's talk about second differences. Yes? The answer is just the sequence because it wants an arithmetic sequence, right? Here it says to write an arithmetic sequence. So it's just that list of numbers separated by commas. Okay, so this one is an arithmetic sequence. And how do we know it's an arithmetic sequence? Because if you take consecutive numbers, right, and you subtract, the difference is 1.3. The difference is 1.3 each time. Okay? Now, sometimes you have a sequence, and when you do that, when you take the difference, they're not the same. So what we did here, right? What happened? Okay. What we did here is first differences. So if you subtract successive terms, that gives you first differences, right? When the differences are the same, we say that it's an arithmetic sequence. Okay? So first differences in this example are all 1.3, 1.3, 1.3. Those are the same, so that's an arithmetic sequence. Okay. So do you remember yesterday when we came up with the formula for AN here? This blue formula is what we came up with, right? But I said that was dependent upon the fact that I labeled this first number A1, then A2, then A3, then A4, right? So my formula was A1, this one, plus N minus 1 times D. Now, what if I started with A0, right? Remember, we fixed it. If I start with A0, then my formula is A0 plus how many of the differences do we add? As many as our n's are, right? So it fixes to A0 plus ND. Remember we did that yesterday? Okay, so we're going to use that definition right now. Okay. So when you have an arithmetic sequence, you have AN is equal to DN plus A naught. A0. Okay, A0, that's a constant, right? N changes every single time. So look, if I were to call AN, I don't know, Y. Okay? And N is changing all the time. N is 0, then 1, then 2, then 3, then 4. So suppose I called N X. Does D change in each sequence? No. D is the same. So suppose I gave it another name, M, because it's the same every time. Does A not change, like A0 change? That's just the first number, right? It's just the first value. Suppose instead of A0, I called it B. Now look at what that equation looks like. Y equals mx plus b, right? And so when you graph it, but now your x is n, so your horizontal axis is n, and then the vertical axis is y or an. So when you graph it, this is what it looks like. So for example, if you go over 1, you go up the same amount. If you go over 1, you go up the same amount. If you go over 1, you go up the same amount. That's how like the numbers would look if you graph them.
We did graphing like that with like never mind. It was like no, actually that's a mix.
Yeah, it is something else.
Yeah.
Okay. All right. So basically, like if I were to graph an arithmetic sequence, I would get a linear graph like this. Okay. Now, what if I have a sequence and I do those first differences and I don't get the same number? I don't get 1.3, 1.3, 1.3, 1.3. So in that case, you can also look at second differences. All right. So let's take a look. And you know what? Every year I don't leave enough room for this problem, but it's okay. Take a look at this sequence here. Write small. N equals 1, 2, 3, 4, 5, 6, and so on. All right? All right, let's do the first differences. What's D here? 8, 10, 12, 14. And then here I have 16. Is this an arithmetic sequence? No, if it was an arithmetic sequence, all these numbers would be the same, like 8, 8, 8, 8, 8, 8, 8. But now, let me take a difference of these. What's 10 minus 8? And 12 minus 10? And 14 minus 12? And 16 minus 14? 2. So look at that. First difference is not the same. Second differences are you have that in common, right? Those are all the same. So now, guess what? When you graph this sequence, so look, n equals 1, what's the value? 12, right there. N equals 2, it's 20. N equals 3, it's 30. N equals 4, it's 40. When you graph this, it's a quadratic equation. It's a parabola. All right? So, what we're going to do is we're going to find a quadratic model for this. And this T shouldn't be there. Okay? So, remember chapter 6? That's what we're going to do here. All right. So, look at what we have here. When n equals 1, what's A1? What's A1? 12. Okay? When n equals 2, A2 is 20. When n equals 3, A3 is 30. All right? So take a look here. Look, this is n, that's the x-axis, and an is the y-axis, right? So if these are like your x's and these are like your y's, if I write them in terms of coordinates, it's 1, 12, 2, 20, 3, 30. Do you guys see that? These are the x values and these are the y values. Okay? So now what I'm going to do is come up with an equation like this. So I need to find A, B, and C. What does that remind you of? That chapter 6 problem.
X squared.
Yeah.
And
Okay, so when n equals 1, right? What's n? N equals 1 here. So it's A plus B plus C equal to 12, right? So I'm going to plug n equals 1, an equals 12 into that circled equation up there. So now I'm going to plug in n equals 2 into the ends. So I get 4a, n equals 2, 4a plus 2b plus c is equal to 20. What do I get when n equals 3?
9a plus 6b plus
3, c. Okay, so now, how can I solve this?
matrices.
Matrices.
No.
Yeah.
Let's go.
So here's what we're going to do. The easiest way is by far by using inverses, right? So 1, 1, 1, 4, 2, 1, 9, 6, 1 times the variables a, b, c equal to 12, 20, 30. So what do I have here? Ax equal to b. And how did I solve for x? Right, it's A inverse times B.
What is this?
What is this? This is chapter 6.
Why are you doing that?
Because I need to come up with this equation to graph this that would give me these points.
Oh, is this not the example number 6?
It is the example number 6. I need to come up with the equation that when you graph it gives you 12 for the first term, 20 for the second term, 30 for the third term.
Is this like something that we'd see like used in more depth?
The higher up you go, yes.
Yeah.
Yes, absolutely yes. Okay, so when you solve for this, B is equal to 1, 5, 6. And that stands for A, B, and C. So my equation AN is AN squared plus BN plus C. So it's N squared plus 5N plus 6. Okay? So now when I graph that equation that I just got, if I add a graph here, all right, so that was N squared, right? X squared plus 5x plus 6. Okay, so this is N, right? And N is your counter, right? Like the first term, second term, third term. So basically it starts from 0 and it goes up, right? So let's go to menu here. And in our window, let's go to window settings and let's put X min to 0. And then when you graph, let's go back. Sorry. Window 1. I'm going to put this to like 50 or 60. Okay. All right. Okay, so here's the equation. All right, so let's trace this, right? Okay, so what was it? Oh, menu, sorry, 5, 1. Okay, so when N is 1, what should my term be in that sequence? 12. So let's do N equals 1, enter, look, it's 12. What about N equals 2? 20. And N equals 3, 30, and so on. N equals 8. Right? It's all the way up there. So with this, you could like extrapolate the entire sequence. Like you could see how like the entire sequence will look. All right? Okay, so this is second differences, huh? Yeah, you can. And the table, you can. Yeah. Okay, let's talk about arithmetic series. Remember we talked about series yesterday. This is when like you add the numbers in the sequence, right? Okay, so if it's arithmetic, you've got like this clear-cut pattern. There has to be a good way to figure out a shortcut for this sum of a arithmetic series. So let's figure it out, okay? You know what? Let's derive some of these formulas. Let's see how we can come up with the formulas to add all of the numbers in an arithmetic sequence. All right, so let's see what we're going to do. Okay, if I say Sn, right, what exactly is that? That's A1, right? That's the first term. Plus, what's the second term? A1 plus D, right? Like how do you write an arithmetic sequence with a difference of d? And then the third one is a1 plus 2d, right? What's the third number? A1 plus 3d, the fourth number, I mean, a1 plus 3d, and so on, right? And then what about the end? So it ends with an, right? What's the term that comes right before it?
An minus 1.
Not an minus, well, okay, so if your numbers are this, and d is 2, right? Okay, so if you go up like this, you add 2, right? But what if you start up from here and now you want to go backwards? What do? You subtract 2. So, so here, your last term is an, right? What's the one that comes right before it? An minus d. And then the one that comes right before that? An minus 2d. Okay, so that's all the terms in that sequence. So that's Sn. Now, you know what? Just for fun, you know what I'm going to do? I'm going to write the series again, but this time in reverse order. Okay, so let's start with the last one, an, plus an minus d, plus an minus 2d, plus, and then here we have a1 plus 2d, a1 plus d, a1. Okay? Now, you know what I'm going to do? I'm going to add these two lines, just for fun. So let's just add them all up. What's Sn plus Sn give you? 2Sn. Now, I align these, and I'm just going to add like top to bottom, right? So first, let's add these. What does that give you?
2an.
Is it 2an?
2an.
Is there a 2?
An plus a1.
It's just a1 plus an. Plus, now let's add this one. What does that give you?
A1 plus an.
A1 plus an. Now let's add these ones. What does that give you? A1 plus an. And now plus dot dot dot. And then if you go here, right? These go away. So you have a1 plus an. These ones, oh my God, look, it's a1 plus an. And then what about the last one? A1 plus an. How many of these parentheses are there from beginning to end? There are 6 in this one,
Infinite though.
but not infinite because it ends somewhere. How many was supposed to be in this sequence and we stopped? So we started from A1 and we ended with AN. So how many are there?
N minus 1.
Not N minus
N.
1, there are N of them, right? So I started with 1 and then I ended with N. So there are N of them, right? So 2Sn is equal to, there are N times A1 plus AN. I didn't, it's 2Sn. It's 2 times Sn from up there. And now, can I solve for Sn? Divide by 2, divide by 2, what's Sn? N over 2, A1 plus AN. So, if you have an arithmetic sequence, if you have an arithmetic series, look, that's the formula to add them up. And that's how you come up with it. You just add the series to each other twice, and you see that that's how it reduces. Okay? Now, let's take this formula back here. Right? Sn is n over 2, a1 plus an, right? Yesterday, did we come up with another formula for an?
Yeah, it's A1.
So n over 2, A1 plus, what was AN? Tell me. A1? N minus 1 times D. And guess what? That's the second formula here. Okay, so that's the second formula. And how did we, was it like was it like some like black magic? No, we just came up with it by substituting one thing into the other, right? Okay, so when do we use each one? So this one, when would you use this one? When you have what, let's say, the bottom one? Right. Huh? So yesterday in here, remember we said A1 is equal to, or AN is equal to N minus 1D, like this one. I just plugged it in there. So this one is useful if AN is unknown. Okay? All right, let's take a look at this one here. It says to find the indicated sum, right? You have a series. It starts with -3 and it ends with 157. I don't know how many there are, but I know A1 and AN. Okay? So what do I know? I know A1. I know AN. Do I know D?
Yes.
Yeah. How much is D? 5. Okay, so which one of these formulas am I going to use?
Second? No. First.
Okay, so do I know what N is?
Yeah.
Do I?
No.
Can I find N?
Yes.
How?
Using the equation.
Right, so I don't know what N is, but I do have an equation for it.
A sub N equals A sub 1 plus.
Right. So 157 is -3 plus N minus 1 times 5. And when you solve this, N equals 33. Okay? So S is N over 2, A1 plus AN, 33 over 2, A1 plus AN, 2,541. If you add all those numbers up. Huh? 15. Where did I get 15?
That's one.
Okay. Okay. This one. Go ahead and do this one. So what do we have here? 17th partial sum. What does that tell you? That's N equals 17. So I want S sub 17. Right? So I'm going to use N equals 2, 2A1 plus N minus 1 times D. Because I don't have AN, so I could use this one. All right, so that's 17 over 2. Huh? Yeah. 2 times 53 plus 16 times what's D here? -22. So S17 is -2091. $16 is D. It's 31 minus 53. No, it's not. 17 minus 1. I'm so sorry. It's N minus 1. So it's 17 minus 1.
3,550.
-2091.
Like a negative, that's why.
Yeah. Okay. So this one. How much is, okay, so look at this one. I have a series here and it goes from 10 to 32, right? So how many total numbers are there if it goes from 10 to 32? It starts at A10 and it goes to A32. How many are there? Is it 22? Huh? It's 23. So look, because you have to include 10. So from 10 to 32, if you don't count the 10, then there are 22, but then you have to count the 10 as well, right? So n is 32 minus 10 plus 1, 23. Because if you start counting, it's 10 to 32 inclusive. So you also count the 10, 11, 12, 13, 14. Yeah. Okay. So what we need to do now, okay, so look at what the formula is. The formula is Sn equals n over 2, a1 plus an. Here's where students usually get sort of like hung up in the notation. What does A1 and AN really represent?
The first.
Right, the first and then the last. So in this problem, the first term,
16.
exactly, it's A sub 10. So that's when 10 plus 6 equals 16, right? It's the first term that you generate from this. So the first thing you plug in is 10, so it's 16. And then the last term is A sub 32, which is 32 plus 6, 38. So Sn is what over what? 23 over 2.
23, 32.
23, because n. Like it's n over 2. It's how many numbers there are.
23?
Huh?
Why is that 23?
N is the number of numbers there are.
Oh, okay.
The number of terms there are.
So you subtract 32 from 10?
And then you add 1. We just did that for like 5 minutes. Okay, hang on. Let me finish this. Uh-huh. Over. Okay, so that's, so Sn is 621. Okay? So